Good afternoon. My name is Marielle Villeray, Program Development Director of Academic Initiatives and Strategic Innovation and Director of Lifelong Peer Learning Program, or LP Squared, at the Graduate Center. Today we are joined by speaker Ellen Zweibel for the concluding Fridays at 1 event of the spring semester. Fridays at 1 is the LP Squared banner series of talks by esteemed guests and organized by members. LP Squared is a non-credit program of study groups that are peer organized and complemented by several member-led committees and activities, events, and volunteer initiatives. If you are retired or partially retired, find out more about our program at www.gc.cuny.edu/lp2. Today's program is made possible with support from CUNY TV and the IER, Institute for Education and Retirement. A moderated Q&A session will follow today's talk, and you can type in your questions at any time throughout the event using the Q&A button at the bottom register of your Zoom window. In addition, following the program, you will receive a survey that we hope you will complete to help inform our future programs and events. Thank you. I now invite Leslie Herman, co-chair of Fridays at 1, to turn on her camera and microphone to welcome you.
Ariel. Good afternoon and welcome to Fridays at 1, which happens to fall this year fittingly on Earth Day. Today's program on the James Webb Space Telescope will honor the memory of a longtime member of IRP, now LP Squared, Norma Grossman. John Gillespie, a CUNY Professor Emeritus of Astronomy and Physics, will introduce Dr. Zweibel. Dr. Zweibel's talk will be followed by question and answers, and John will moderate. John himself leads popular study groups at LP Squared on astronomy and on science and literature, and I have personally taken several of them, and they're quite wonderful. So please welcome John Gillespie.
Good afternoon. Today's talk is in honor of Norma Grossman. Briefly, Norma was a very active member of the IRP, the name of the LP Squared before our recent change. And she taught biology in high school for 25 years, followed by nearly 25 years of membership in the IRP. She was extremely active. She took over 100 study groups and coordinated over 40 over an extremely wide range of subjects. She was exceptionally talented and dedicated teacher. She loved science and sharing her enthusiasm for it. In the IRP, she inspired members to take science for the first time and convinced them that science is accessible. She was a very creative colleague and friend. The importance of models, role models in science, particularly for women, is becoming better acknowledged. And I should mention that her daughter, our speaker today, Ellen, has classes in the University of Wisconsin, Madison, in astrophysics, and in those classes, nearly 50% of the students are women. So there is progress being made. Ellen took her bachelor's degree in mathematics at the University of Chicago, then her PhD in plasma and atmospheric at Princeton, and then her field has always been astrophysics and plasma physics, and she became professor at University of Colorado. She was a founding member and the former director of the Center for Magnetic Self-Organization for the National Science Foundation and the Department of Energy. She's now the Kraushaar Professor of Physics and Astronomy, as well as the Vilas Distinguished Achievement Professor at Madison for the University of Wisconsin. In 1991, she was elected a Fellow of the American Physical Society. In 2016, she received the James Clerk Maxwell Prize for Plasma Physics. And in 2021, she was elected to the National Academy of Sciences, the nation's highest scientific honor. So this is a particularly important time for astronomy. We're at the transition between two eras, the Hubble era, which has been operating for at least 30 years, and the Webb telescope, which is very likely to see its first light, that's the term for the first image coming from a new telescope, in the next 60 days, if all goes well. It should be mentioned that this extraordinarily complex and complicated device, whose assembly is extremely challenging, is every element of its components and their harmonious synchronization has gone at least as well as expected. We should point out that you cannot go there and make tune-ups. The Hubble was able to have a contact lens imposed, but that you can't do. The Webb is currently 1 million miles from Earth. Now, you may, if you're not familiar with telescopes, you may wonder, why do we want bigger telescopes? And the quick answer is from the old song, Long Ago and Far Away, meaning that a larger telescope sees fainter light, which could be coming from more distant sources. And therefore, it's a time machine. It's allowing us to look back in the history of the universe. And with a larger telescope, such as the Webb, the age of stars and galaxies that can be measured are even farther from Earth, and the resolution is significantly better. So we are now exactly at the transition year between having the Hubble and, as a complement and a successor, the Webb. So let us now hear the telescope described by Ellen.
Hello, everyone. Can you see me? Can everybody see me?
We can, Ellen, and we see your screen.
Great. Okay, so I'd like to thank you for this invitation. As John mentioned, as Leslie mentioned, Norma Grossman was my mother, and I think very few people get to honor their parents in this way. So I really thank you. I thought I would begin by telling you a couple of things about my mother that maybe not even her best friends know. So Mom was a whistleblower. This image here, can you see my cursor? No, sorry. Sorry, I may have to just show it like this. This never happens. Yeah, so Mom was a whistleblower. When all of us were in school, she got a part-time job as a lab technician. And part of that job was to test the water in the local pond, Lake Toponimus, that we use for swimming. And when she looked at this water under a microscope, she discovered that it was just teeming with bacteria. There were a lot of farms in the area, a lot of runoff. And let me just say that this was a bucolic scene in a way that nobody had really recognized before. So she refused to certify that it was safe for swimming. And she went toe to toe with the director of the lab, and the water was certified and she was fired. So she was fired for her principles. There was at least one family that was not allowed to swim in Lake Topanemus. She and my dad always had faith in my ability to do science. Sputnik was launched beginning the space race when I was in kindergarten. And I remember Mom said when I came home from school that day, she said, "You're going to get a lot more science in school now." And she was right. I was part of the workforce that was trained to compete. She lived independently as long as she could in Brooklyn. But in July of 2021, she moved to Longmont near her son, Marty. And on September 2nd, she turned 92. And here she is with Marty, my brother, and my sister-in-law, Joyce. And she passed away two days later in her sleep. And, you know, she loved the IRP and she made many friends there. I've had the privilege of meeting many of you, including John. And I'm just so sorry that her last years were blighted by the pandemic in the way that they were. So John told you something about James Webb. Let me begin with a timeline, because I think NASA and maybe even the astronomical community had egg on its face for quite a while. So in 1989, 1 year before Hubble Space Telescope was launched, there was already a meeting to discuss the next big thing, the next big telescope in space. And at that time, astronomers made the case for a telescope with a 10-meter mirror, 30 feet, that would be sensitive to infrared light. I'll talk about the advantages of infrared in a few minutes. 10-meter infrared telescope in space, 1989. So Hubble was launched, Hubble was repaired, and in 1996, there was sort of an official beginning to the construction, the planning of this telescope. It was called the Next Generation Space Telescope. And in 2002, it was renamed for James Webb, and I'll go into that in a couple of minutes too. The first contract for building James Webb Space Telescope, JWST, was awarded in 2003 to an aerospace company called TRW. It was $125 million, and the anticipated launch date was 2010. In 2016, the construction of James Webb was completed. A launch was planned for 2018, but it was postponed due to serious technical issues. There was then an increasingly accelerated cadence of scheduling and postponement. Finally, on Christmas Day of 2021, it lifted off flawlessly from the Guiana spaceport in South America. I know of at least one astronomer, a young assistant professor, colleague of mine, grown man, burst into tears. I didn't cry, but I was kind of walking around the house like a cat. And as John indicated, it is working perfectly. This is an image of a test star. It's an artificial star. And what's important about this image is that it's absolutely clear. It's not false in any way. It shows what it's supposed to show. And this is a sign that the mirror of this telescope, which was actually assembled and aligned out of 18 pieces, and it's shaped like this. It's kind of a series, it's like a honeycomb. It's like a series of hexagons put together, that they were perfectly aligned to better than the thickness of a human hair. The telescope has a sun shield And the unfurling of that sun shield was an incredibly complex operation. That's one of the things that delayed the launch so much. The sun shield is to keep it cold, and the orbit is to keep it cold too. So as John indicated, JWST is 1 million miles from Earth at a special point relative to the Earth and the sun called the second Lagrange point. And that point will keep it shielded in perpetuity by the Earth from the sun. And the sun shield and the L2 placement are necessary because in order to observe in the infrared, you have to eliminate all competing sources of infrared radiation. And we are radiating infrared constantly. So you've probably seen pictures, infrared glasses, everything glows. And the telescope has to be cooled to virtually absolute zero to avoid competing with the very faint cosmic radiation that we're trying to see. So the final launch, we were up to $10 billion from 825 million. The operating costs are about $130 million a year, and significant funding was put into the telescope by the European Space Agency and the Canadian Space Agency. So how will we observe with JWST? So the telescope by itself, the mirror that you saw, is really just kind of a big bucket of light that gathers light the same way our eyes do, but in much greater quantities. And then you need to analyze and record that light in some way. And so there's this so-called NIRCam, the near infrared camera, which will actually take images in infrared light. This was built by a team at the University of Arizona, led by Professor Marcia Ricci, one of the few major instruments built by a team headed by a woman astronomer. Marcia is a real pioneer. There's the MIRI, the mid-infrared instrument, which will do two things. It will also take pictures at an even longer wavelength, and it will split the light by wavelength, kind of like a prism, creating a so-called spectrum. Then there's a third, so that was built by the European Space Agency. Then there's a third sort of dual functioning instrument, the fine guidance system / near infrared imager and spectrograph, too long to write out, that will image and split the light and guide the telescope. And that is the Canadian contribution. And unlike Hubble Space Telescope, which has been spectacularly successful, still in use at more than 30 years after launch, it's been repaired, it's been serviced. James Webb, because of its placement, is too distant to be serviced, and it's estimated that the lifetime is only 5 to 10 years. So what is the cost of this enormous delay, which in retrospect, since it's working perfectly and not everything we've put into orbit has, the delay was worth it. So it was economic activity. People went to college. Kids went to college on their parents' salaries for making JWST and so on. The delay in James Webb really cost a generation of astronomers its use, the 12-year delay. So Marcia Ricci will do some observing with JWST, but she will probably retire before the telescope does. On the other hand, young astronomers like Ke Zhang, assistant professor in my department, one of our recent hires, who was just starting her undergraduate career at the time James Webb was supposed to be launched, will be there for some of the very first observations. So one generation has passed the torch to the next. So let me talk a little bit more about James Webb. So John covered this beautifully. James Webb sees into the past by allowing us to see objects when they emit a light that's only now reaching us. So the most distant galaxy that we have now seen, the light left that we are seeing now left 13.5 billion years ago. when the universe was still very young. Next question, why infrared instead of visible light? Well, it's because as the universe expands, as illustrated here with this stretching of a rubber band, light is stretched to longer wavelengths as it travels through the expanding cosmos. Here's an image of the electromagnetic spectrum. This little rainbow here is the tiny fraction of it that the human eye is sensitive to. Over here, you've got your long wavelength radio waves. Here, you've got your short wavelength gamma rays. This is what we see. And the light from this 13.5 billion year galaxy is stretched from being emitted here in the ultraviolet, where we can't see it, to here, the far infrared, where we can't see it either. So the way to see galaxies as they emit light is to look at these very long wavelengths. A couple more questions. So if we have to observe at the infrared, why can't we do it on the ground? Because the water vapor in the Earth's atmosphere absorbs infrared radiation, makes it much harder to detect astronomical sources. And I already explained why the telescope has to be kept cold, because otherwise its own infrared radiation would overwhelm these faint cosmic sources. So why did James Webb cost more than 10 times what it was projected to cost and take so much longer to develop than planned? Well, frankly, the very ambitious technology needed to realize it was just not ready. I was part of a recent study by the National Academy. This happens every 10 years, a decadal planning report for astronomy. And with James Webb very much on our minds, we called for a technology development program to anticipate the future needs of the space program so that we don't start things when we don't know how to finish them. And we hope it works. And finally, who was James Webb? Well, he led NASA from 1961 to 1968, which was the Apollo moonshot years. He was not a scientist. He had a background in business, in law, in government service. He worked for the State Department. But he believed in the value of science, and he actually elevated the roles of scientists at NASA, and he promoted a very robust space program that we're really still reaping the fruits of. So Hubble Space Telescope launched in 1990, but the planning goes back many, many decades. Now, James Webb and the naming of the next generation space telescope after James Webb has become embroiled in controversy because his record is mixed. So in the 1950s and 1960s, there was a general attempt to fire federal employees for their sexual orientation. And he seems to have not only participated in this, but been pretty avid about it. And it caused, tremendous human suffering. It lost talent, and it deadened the workplace climate for the people surrounding the people who were fired. It created a climate of suspicion, a sense of being watched that is very bad for creativity and for a harmonious workplace. And there are some alternatives on the table. Harriet Tubman navigated her way to freedom, following the stars. Sally Ride, I'm getting all choked up here, I'm sorry. Sally Ride, the first American woman in space. These are people we could name the telescope for. Okay, so let's go on to the science. So what might we see? So as John mentioned, the bigger a telescope is, the smaller the angles that it can resolve. And here's an image of this great nebula in Andromeda, also known as M31, the closest Milky Way-like galaxy to the Milky Way itself. And if this galaxy were placed at the distance of the most distant galaxy that we now know, that one that we are seeing as it was 13.5 billion years ago, we could see structures in it of this size. So we could see what we now see as a kind of a fuzzy little blob. And what we could see is an image much more like this. James Webb will be able to explore the formation of planets, and it will observe, it will be able to penetrate, because of being able to see in the infrared, it'll be able to penetrate very close to the Milky Way supermassive black hole, a region which is so opaque that right now we can only see it in infrared and radio. So that's at a sort of very basic level what James Webb can see. So let's drill a little deeper. And I'd like to begin with kind of an inventory of the universe. So if we break the universe down into the different forms of energy that it contains, about 5% of that is ordinary matter, like us. And by ordinary matter, I mean that it generates and responds to gravity, and it emits, absorbs, and scatters light. About 27% is so-called dark matter. Dark matter generates gravity, and it responds to gravity, but it does not interact with light in any way. It doesn't emit it, absorb it, or scatter it, and that's why it's dark. But the lion's share, about 68%, is something that we call dark energy. Dark energy does not interact with light like dark matter, but instead of responding to gravity and generating a gravitational force the way we think of matter doing, it exerts some kind of repulsive force that accelerates the cosmic expansion that began with the Big Bang. So up until the discovery of dark energy, we sort of thought of the expanding universe as something like a ball that's thrown into the air, and as it begins with a high velocity and then it slows down due to the pull of gravity, maybe comes back, maybe keeps going, but always more and more slowly. So this was a total surprise, and the kind of elephant in the room for everyone who does astronomy, like people like me who don't necessarily work on dark matter or dark energy, is that there is this stuff out there. There's dark matter, there's dark energy, could engulf us at any time by this sort of tidal wave of new and unknown physics, which is exciting, but most of the time I don't think about it. I just do my own thing. But let's talk about how we even know about dark matter. So on the left is an image of a so-called cluster of galaxies. So every fuzzy patch that you see here is a galaxy, all at about the same distance from us, many millions of light years. And they're congregated into this large cluster held together by gravity. And this purple haze here is a representation of gas which is so hot that it's glowing in the X-rays, gas that's at tens of millions of degrees. And the fact that this cluster of galaxies and hot gas stays together despite all the energy in the hot gas and in the motion of the galaxies is an indication that the gravitational field in this region is much, much stronger than the visible matter alone would provide. The galaxies attract each other, the hot gas attracts the galaxies, but if you add it all up, it's far from enough to account for all the energy we see that's opposing it. And so this led to the first sort of quantitative prediction many decades ago that there is some form of dark matter in galaxy clusters and in galaxies. And we have even more beautiful direct evidence of this through the so-called gravitational lensing phenomenon. So here's another image, another galaxy cluster, also imaged. And I've drawn this kind of palsied looking red circle around this kind of arc that I would like to draw your attention to. And what this is it's the light from galaxies that has been split up because it's passing through warped space. So according to Einstein's theory of gravity, massive objects warp space, kind of like if you put a bowling ball onto a rubber sheet. And then the path of light through that warped space is very irregular, just like the path of light through a thick piece of glass. That's why it's called a gravitational lens. And many observations of gravitational lensing through galaxy clusters and even near individual galaxies have given us a portrait of dark matter that is very precise despite our inability to see it. Dark matter plays a very important role in cosmology and the formation of galaxies and galaxy clusters. We can do big computer simulations of the evolution of dark matter over time. So this series of 3 cubes goes from 13 billion years ago. It's 3 snapshots, 13 billion years ago and now. And we began the computer simulation with just many, many points of dark matter, and we let them interact under their own gravitational attraction, and they formed this so-called cosmic web of dense sheets and filaments that has just become more and more, kind of bifurcated over time. And every one of these little dots where there's a lot of dark matter and gravity is very strong, it's a potential attraction point for ordinary matter and forming a galaxy. And one of the things that I love about being an astrophysicist is the universality of physical law. So not only do we have dark matter operating on scales of billions and billions of masses of the sun, here is a little asteroid called Ida, and this little dot here is its moon, Dactyl. Ida is about the size of Long Island, and Dactyl is about the size of Manhattan. And there's no other gravity out there for Dactyl to feel, so it's in orbit around Ida. The same forces that have caused this dark matter to coagulate over 13 billion years. So there's been a lot of theorizing about dark matter, and we think it's some kind of particle, and there are laboratory experiments on Earth to try to detect it. And here's a schematic of one. This is one possible candidate dark matter particle called a weakly interacting massive particle, or a WIMP, and it's coming into this detector here, and every now and then it will knock off some electrons and they'll be detected. There are astrophysical searches. Even though dark matter itself is dark, there are candidate particles for dark matter in which every now and then a dark matter particle decays into something that we can see. Maybe it makes gamma rays, maybe it makes electrons, anti-electrons or positrons, neutrinos, protons, antiprotons, some chance of seeing the decay products of dark matter. And between the laboratory searches and the astrophysical searches, this is a big growth area for physics. This graph just shows from 1997 to 2011, the growth in the number of physicists in the United States and beyond that are working on dark matter. As I was putting this talk together, I realized that 4.5 years ago, I went to a talk by a well-known cosmologist. I won't name him because I don't know if he want to be quoted, but he said, if the dark matter particle isn't found in the next 5 years, it will be a crisis for physics. So we have 6 months to avoid this international crisis of physics. So how can JWST shed light on dark matter? Well, James Webb can search for the very faint light that might be radiated by the products of dark matter, decay, push the sensitivity to a new level. Look for evidence of the distribution of dark matter through gravitational lensing from much more distant sources seen much longer ago. See dark matter being put together. And as a complement sort of to this second idea, to see where galaxies are actually forming and trace the cosmic web very far back in time. So just to remind you of these three images, but these are just three ideas. They'll have to, there's always more. People are always thinking, people are endlessly inventive, and there will be all sorts of new ways of tracing dark matter with James Webb. Now, how about dark energy? So to talk about dark energy, I'd like to talk about, introduce you to the concept of a standard candle. So this is a portrait of Henrietta Leavitt. She was an astronomer who worked at Harvard College Observatory. She died at the age of 53. She did something very important before she died. She attacked this general problem of how do you know how far away something is if you don't know what it is? So a colleague of mine used to do this with teddy bears of different sizes for his astronomy class, but I didn't do it with teddy bears. So there's a dwarf satellite galaxy of the Milky Way. It's only visible from the southern hemisphere. So people who lived in the southern hemisphere, of course, knew about it for a long time, but the first European who discovered it, who viewed it, was Magellan on his voyage, and it is named the Large Magellanic Cloud, or Cloud of Magellan. There's also a small one, so two dwarf satellites of the Milky Way. And she observed a type of star, observed and monitored a type of star in the Large Magellanic Cloud called a Cepheid variable. So this is time, this axis here, and this is brightness according to an astronomical scale. And it varies very regularly by quite a lot. And this is called a Cepheid variable star. So the prototype is a star called Delta Cephei. So Cepheus is a constellation, and Delta is the fourth brightest star in the constellation Cepheus. So she observed a large number of these Cepheid variables in the Large Magellanic Cloud, and she figured that although she didn't know how far away the Large Magellanic Cloud was, we now know that it's about 150 million light years. She assumed that since they were all in the same place and all associated with this bright object here, that they were all at about the same distance. And she discovered that there was a correlation between the average brightness of a Cepheid variable and how long it takes to go through a cycle. So here is one cycle. And if you make a plot of average brightness versus the period, you get this very nice tight correlation. So what she realized is that you can gauge the intrinsic brightness of a Cepheid by measuring its period. And this was a very important, and I believe the first example of a so-called standard candle. So a standard candle is an astronomical object which has a known brightness. And by comparing the brightness that you know it has with the brightness that you see, you can tell how far away it is, because brightness falls off according to an inverse square law. And so then she went backwards. She found Cepheid variables in the Milky Way, and there were some local distance indicators, and she filled in a couple of rungs on what's called the cosmic distance ladder. So very important concept and pioneering work. So it turns out that there's a much brighter but more rare standard candle, and that's a certain type of supernova. So you have to do a little more processing and massaging of the data, but Saul Perlmutter was able to put a whole bunch. So in a galaxy like the Milky Way, there's one supernova about every 50 years or every 100 years. So how could you, put together enough statistics about a supernova based on one galaxy? Well, supernovae, which are the complete explosions of stars, are so bright that you can see them in very distant galaxies, a large fraction of the way across the universe, and have enough supernovae to establish statistics. And he showed that there's a way of making them into standard candles. So they started measuring cosmological distances far beyond anything that had ever been done using these supernovae standard candles. And after several years of observation, these three guys, and of course, many people who work with them, were kind of led kicking and screaming to the realization that space is not expanding in the way everyone expected. So, as I said a few minutes ago, we think that after the Big Bang, the universe was expanding extremely fast and it's been slowing down. Well, the only way to reconcile the apparent brightness of supernovae with their distances and with the expansion of space, is if the expansion of space is actually accelerating. So they discovered dark energy. And this was so important that they shared the 2011 Nobel Prize in Physics. So this is Saul Perlmutter, Adam Rees, both American astronomers, and Brian Schmidt, Australian. And it's now more than 10 years of accelerated expansion of the universe. And we haven't really found a way out of it, although we've looked at the data very, very skeptically, because part of being a physicist in good standing is not to just, sort of keep introducing new laws every time there's something you can't explain. You try as hard as you can to explain everything using what we already have. That's just kind of the aesthetics of physics, but this really did seem to call for something new, namely dark energy. So just to recap, the universality of gravity predicts that the expansion of the universe should be slowing down, but there is this mysterious force that's pushing the cosmos apart, and that's what we call dark energy. Now, unlike dark matter, where we have some candidate particles that we can look for in the laboratory, we really don't have a clue what dark energy is. Is it some kind of particle? Is it some kind of field that's not a particle? What is dark energy? We don't know, but it seems to be necessary to explain not only the supernova brightness distance relation, which I mentioned, but a few more kind of independent and fairly arcane observations that I will not go into. So we're really in the dark on dark energy, and James Webb will allow us to extend the supernova test and many other tests much farther back in time and really trace the expansion of the universe going further back in time. And this will set some sort of constraint or expectation about the nature of dark energy. Unfortunately, that is all I can say right now. So we're really just kind of at the dawn of dark energy. So a theme throughout this talk has been that observations of ordinary matter reveal exotic matter. And my own little corner of astrophysics is kind of an example of that. So, you know, we're just so used to the Earth having a magnetic field. We couldn't use a compass if we didn't have one. So there's magnetism. The sun has magnetic fields that show up as sunspots and power solar flares. And sometimes the solar flares create storms on Earth that knock out communication. So planets, stars have magnetic fields. It turns out that the galaxies have magnetic fields too. So here let me talk about the image on the right first. This is a nearby galaxy, number 82 in the Messier catalog. And like the Milky Way, it has a disk, but it has this huge blowout of gas that's coming from the center. And what seems to be going on is that there was very intense star formation here near the center of this galaxy. It's a so-called starburst galaxy. And the energy from the many supernovae that resulted from forming all those stars is just blowing gas out of the galaxy. This is called a galactic wind. And it turns out that this gas has a magnetic field in it. And what you're seeing here is just the central portion of this galaxy imaged in the infrared, which gives us a completely different view of it. So here is the brightest infrared radiation, less bright, even less bright. And what we did here, and I was actually involved in the creation and interpretation of this image, you see these little wisps here, these little turquoise wisps. They represent the orientation of the magnetic field in this galaxy, seen in polarized infrared light, just like polarized sunglasses. We can learn something about magnetic fields from the polarization of light. And the magnetic field is being dragged out of the galaxy in this way. So we don't know where magnetic field, how the universe became magnetized in the first place. That, despite all the progress and everything we've learned about cosmology, we don't know that. We don't know why the universe is magnetized. And that's kind of my little corner, how magnetic fields originated, how they evolve, and some of the phenomena that they cause in ordinary matter, things like solar flares and sunspots. And I'm able to do my work by ignoring the fact that this tidal wave of dark energy might be about to break over my head and change everything. And that's just how humans carry on. So, astronomers live in the past. We see things as they were. I love this quote from William Faulkner: "The past is never dead. It isn't even past." He said that in a story called Requiem for a Nun. And so my brother sent me a scan of this wonderful picture earlier in the week. This is my mom when she was about 18 years old. This is my dad when he was about the same age. He normally wore thick glasses, but I'm sure they said, "Johnny, take your glasses off to have your picture taken." So here he is, here she is. Here's her younger sister, my Aunt Selma, would have been about 11. And her parents, my grandparents. Look at that hat, Elsie and Abe Cutler. He was Ukrainian. She was from a part of Hungary that's now in Romania, Transylvania. He came to the West through Poland, as many people are doing now. It was different times. He had saved a little bit of money as an apprentice to a tailor and paid a farmer to smuggle him into Poland. under a load of hay. So that's how we got here. So thank you. And now I'm very happy to take your questions.
If you want to ask questions, on the bottom of your screen, you will see a Q&A icon. And if you click on that, you can leave your questions. Don't use the chat. It shouldn't be there. And so on any subject that Ellen has touched on or related, your questions are welcome. We have one question from Dan Kozlow, who would like to know the annual operating costs of this system.
So what does that $130 million pay for? So a large part of it is salaries of the people who monitor the instruments, the people who communicate with the satellites, the people who manage the data as it comes down in usable form. There's not that much that we can do to maintain it because we can't go there. The lifetime of the mission could be extended if we could add coolants. So there's a cryogenic, in addition to the sun shield and living in the shadow of the Earth, there's a cryogenic system that makes the telescope even cooler and is necessary for its operation. And that and the fuel that is needed to keep it, so every now and then, so I wasn't complete. You might have seen some solar panels on that sun shield. So despite being in the shade, James Webb also gets its energy from the sun. And so it actually kind of putters around that L2 point just enough to give it a little bit of sunlight. And so these things are all under mission control. So at this point, most of it is people. Does that answer your question?
Okay, we have another question from Ron Florenza. Is the universe expanding uniformly in all directions?
Oh, yeah, that is a great question. So as far as we know, it is. What that means is that any place that you went to in the universe to view the expansion, it would look about the same. Now, for that to be true, it's not true in detail. I mean, we are not expanding along with the universe. We're held together. The Earth is held together. The solar system is held together. So there are local concentrations of gravity and, in our case, chemical forces that are holding everything together. But if you average over a large volume of space, we still think that this is true. So for example, the universe is not rotating around some axis. Now, one of my colleagues, Amy Barger, who I think is rather skeptical of this dark energy idea, thinks that a very large volume of the universe, which happens to be the one we live in, is a little bit less dense, has a little bit less matter in it than the average, and that this is causing it to expand faster than predicted. So that is a possible solution for dark energy. But, I mean, some of these things we think, we can't falsify them, but it's really just kind of a tenet that we cannot falsify of our cosmology, that the expansion looks the same on the average from every point. But we think it does. Does that answer your question?
Okay, we have some other questions. What is the international organization for dealing with the research involved in the Webb?
So it's a kind of shared responsibility by several different organizations. So there's no treaty that governs James Webb the way there is, say, for the International Magnetic Fusion Test Reactor, ITER, that you may have heard of. So NASA is the United States agency, National Aeronautics and Space Administration. The European organization is called ESA, European Space Agency, and the Canadian, guess what, is called CSA, the Canadian Space Agency. And that is kind of who organizes the thing, but it's not a treaty. It's an agreement and a contract. So James Webb, actually, Congress was at the point of canceling it in 2011 because, as I had indicated, the original launch date was 2010, and it was clear in 2010 that they were nowhere near being able to launch. They were still 6 years away from even completing construction. So Congress was at the point of canceling it. And it took powerful political support as well as the astronomical community to kind of rally and keep it in the budget. So the money for NASA is authorized by Congress.
Okay. Now a question about the wavelength of the light and the distance we can see into space. Is the current visible light limitation 13.5 billion light years? Is there an estimate for the limitation for infrared telescopes?
So the universe, 13.5 billion years ago, the universe was only a few 100,000 years old. So when we started observing, we started detecting these very distant galaxies, that was a learning experience in itself, that galaxies even existed at that time. So one of the important discoveries, which I should have highlighted more, is just how early in the structure, in the history of the universe, stars and galaxies came into being. So it is expected that James Webb will see the very youngest galaxies as they form as soon as they have enough stars to be visible. And we don't know exactly when that is, but we're sort of running out of time. We're by astronomical standards, we're almost back to the Big Bang, a few 100,000 years after the Big Bang. So that will be probably the farthest that we can see. So right now, 13.5 billion light years. I don't know what it would, we can't get to 14 billion. There was no before.
Okay, here's a question that basically asks about the fact that your work is related to magnetic fields. Why is it that electrical energy doesn't seem to be as significant?
Yeah, that's a great question. So we see magnetic fields. Why don't we see electric fields to the same degree? So there are electric fields in space that accompany magnetic fields. They are much weaker, and there's a there's a fundamental difference between electric and magnetic fields, which is that you can follow an electric field back to its source within which there is no electric field. So if you could have just one electron out there in empty space, there would be a field around it that would point right back to the electron, and there it would stop. And if you tried to follow that electric field, say it's pointing into the electron, if you tried to follow it out the other side of the electron, that electric field would also be pointing toward the electron. So those lines that trace the electric field are ending. As far as we know, there is no counterpart for the magnetic field. Magnetic field lines do not end. Now, this, we don't take this on faith. There have been searches, experimental searches for the magnetic counterparts of electrically charged particles. And so far, nothing has turned up, but that doesn't mean it won't. And if it does, we will have to kind of rethink electrodynamics. So right now, what happens if you try to, according to our current understanding and with some laboratory evidence, if you try to set up an electric field, electrons will just kind of zoom towards it or away from it, depending what direction it's pointing in. This is how battery works. So you have positive charge on one side, negative charge on another side, creates a flow of electrons, which is an electric current that does whatever you want that electric current to do. Does that answer your question?
Okay. The next question, I don't know what it means. Have you ever watched Dr. Becky on YouTube, and do you like her approach to astrophysics? Do you know who she is?
I do not know who Dr. Becky is.
Oh, then we'll leave her.
Well, if somebody could send me a message who Dr. Becky is.
Do magnetic fields interact with dark matter?
So if dark matter works the way we think it does, no. Because that would mean that in order for dark matter to respond to magnetic fields, it would have to have an electric charge. And if it had an electric charge, that would kind of open the door to interacting with light. So light actually has its own little electric fields. So as far as we know, dark matter is immune from magnetic fields.
Okay. The next is asking, apparently, that we are looking with this telescope at portions of the universe as they were 13 million years ago. So that was in the early universe. Can we extrapolate to where they are now?
Yeah, that's a great question. So I showed you a computer simulation of just dark matter. So there are other computer simulations that put in ordinary matter. And what those very ambitious computer simulations do is they try to follow the formation and evolution of galaxies from the earliest times to the present. And if you look at these computer simulations, you see, the galaxies kind of started out as blobs, and then those blobs kind of got together under mutual gravity and regularized themselves. And at some point, maybe several billion years ago, they already looked pretty much as they do today. Now, there's a wonderful program here at the University of Wisconsin called Undergraduate Research Scholars, of extremely smart kids who are members of underrepresented minority groups. And every year I try to work with at least one undergraduate research scholar. So this year it's Quinn An Lê has a Vietnamese background, and she is going through one of these computer simulations and measuring certain properties of these young galaxies that and trying to see when a particular kind of brightness, sort of a pattern of brightness, try to see when that appears in the computer simulation. And our hope, and actually our expectation, is that we will be able to observe with James Webb and check the cosmological simulation against what we actually see. And I'm working with one of my colleagues who is an expert observer. I don't actually use telescopes, but she has been awarded some observing time with James Webb. And we're hoping that within the next couple of years, this will kind of come together. So right now we're doing some kind of test extrapolations and the ability to check their reliability. So if the computer simulation and reality agree, that will give us more trust in the computer simulation, and we can ask other questions about it. If they're completely different, we'll know that some ingredient in the computer simulations some key ingredient is missing, we've gotten something wrong, have to go back to the drawing board and improve the computer simulations until they're in better agreement with reality.
Okay, a question is there evidence that dark matter and dark energy interact in any unique way with gravity?
So dark matter, as far as we can see, dark matter is subject to the same laws of gravitation as ordinary matter. And that cuts both ways. It exerts a gravitational force and it responds to a gravitational force. Dark energy, no. Dark energy seems to be immune to gravity, and it seems to, instead of attracting, so when you have a concentration of dark energy, it doesn't pull stuff in, it pushes stuff out. So it's really a completely different beast. And that's part of what makes it so mysterious.
Okay, other questions? Oh, what would you speak to the fourth state of matter, the plasma?
Yeah.
What is it? Who knows about it?
So plasma, so in an ordinary gas, like the gas in the room you're sitting in, so that's made of atoms that have kind of congregated into molecules. So mostly nitrogen molecules and oxygen molecules. If you add energy to that gas, you can break those molecules apart into nitrogen atoms and oxygen atoms. If you add even more energy by heating the gas up, so an atom consists of a nucleus, which is positively charged, contains protons and neutrons, surrounded by electrons that are you can kind of think of them as being in orbit. You can also think of them as being kind of fuzzy and filling out a cloud. And if you keep adding energy to a gas, those electrons can escape the electrostatic attraction of the nucleus, and they just become kind of free floating. They don't belong to any nucleus. And a gas of positive and negative charges is a plasma. And what makes a plasma different from an ordinary gas is that it responds to electric and magnetic fields much more strongly than an ordinary gas does. So right now, if you happen to have a compass, maybe your cell phone has one, if you pulled out your compass, you could measure the magnetic field of the Earth. And it would point, if your compass is reliable, it would point the way it's supposed to point. If you put on a, I don't know, asbestos suit or something and ionized all the gas in your room, that gas would actually want to expel any magnetic field, would not want to let any magnetic field in. So that's an example of how you can tell a plasma from, or an electrically conducting gas from a gas that's not electrically conducting. And the reason that magnetic fields are so important in astrophysics is that most astrophysical systems are plasmas. So the atmosphere of the sun is largely ionized. It's a plasma. The interior of the sun is a plasma. If you look, well, you're in New York, but if you go someplace where you can see the Milky Way in the summer, on a summer night, you know, and it's all dark and patchy, what you're seeing is gas in the disk of the galaxy, and that's a plasma, and it hangs on to its magnetic field the way you saw with that starburst galaxy, Messier 82.
What are some of the entropy aspects of dark matter and energy?
Okay, so for dark energy, I'm not going to even hazard a guess, okay, because we know so little. I personally, and I think this, I'm speaking for the scientific community, dark matter, you can talk about the entropy of dark matter. And there's something called cold dark matter, and there's something called warm or hot dark matter. And what this refers to is the kind of average speed of dark matter particles. So if it's very low, it's called cold, and if it's higher, it's hot. And hot dark matter has more entropy than cold dark matter. And ordinary matter and dark matter can influence each other's entropy. So if gas falls down into a dense concentration under the pull of dark matter, as you saw for this galaxy cluster, that increases its entropy. And if you put a lot of ordinary matter together and you kind of reverse the roles and dark matter would fall into the ordinary matter, you would increase the entropy of the dark matter.
Okay. Who has access to the web? How will time be partitioned?
Yeah, that's a great question. So there are a few so-called legacy surveys. You may have seen an example with Hubble. There's something called the Hubble Deep Field, which was just a very long exposure of a patch of the sky made with Hubble over a long period of time. And it revealed an enormous number of faint galaxies. We learned a lot from that image. And that was kind of an executive decision within the NASA management to devote a portion of the time, observing time of Hubble, to creating this deep field. So there will be similar things with James Webb. But otherwise, astronomers, you know, anyone really can write an observing proposal and say, you know, I would like so and so much time on James Webb to carry out this science. And your proposal will be reviewed and rated by a panel of astronomers. They will try to find astronomers who, with expertise in the particular area, you know, maybe exoplanets, maybe galaxies, whatever you propose in, and time will be awarded on a competitive basis. But the data that's gathered by James Webb, all of it, will be in the public domain after a certain period of time, I think about 18 months. And this was done, this started being done in the 1980s with all NASA data because, the stuff is, we're all paying for it. It's all taxpayer funded. And people would sometimes, with really the best of intentions, they would observe with whatever NASA facility it was. And then, life would intervene and they would just kind of sit on the data, and it would never, the results of their investigation would never be published. And it was all, just kind of bottled up. So NASA created this rule that when you take data with a national facility like James Webb or Hubble, you get 18 months that are proprietary when only you have access to the data. But after that, anyone can request it. So you could go into the Hubble archives right now and extract data. Anyone can do that. But that data was gathered on the basis of a competitive proposal.
Another question, what about the future of terrestrial astronomy?
Okay. So the largest telescopes that are currently on the ground have maybe about 10 meter, about 30 feet diameter. One of them is in South Africa. It's called SALT, the South African Large Telescope. And my university, the University of Wisconsin, is one of the main partners in a consortium that operates the SALT telescope. And we actually just finished a device for taking spectra with SALT, and it's actually on its way to Cape Town right now. Huge job. Anyway, so now a new class of telescopes is in the early phases of construction. These are called extremely large telescopes. And we're talking now about mirrors 30 meters, so close to 100 feet in diameter. And this is not a single piece of glass. It's many pieces of glass fit together. So some of these have been approved. You may have read about this because there's been enormous press coverage and it's a long ongoing controversy. There is a project called the 30-meter telescope, the TMT, that the conceivers of the TMT would like to build it in Hawaii on Mauna Kea, where there already are a lot of telescopes. And it's become very contentious. There's a large group of Native Hawaiians who say enough is enough. Mauna Kea has traditional, religious, and cultural significance. And, there's already so much up there, and, it's going to begin with building this enormous road, and, trucks are going to be, coughing and belching their way up there for years to build the TMT, and we don't want it. Permission is denied. And it's still tied up in court. I don't know which way it's going to go. And it's actually kind of split the astronomical community between people who say, it would be such a great instrument and this is such a great place for it, and other people who say, well, we have to respect these other interests. So I don't know what's going to happen. If the TMT is not built in Hawaii, good chance it'll be built in the Canary Islands on La Palma, where there are also a lot of telescopes. But the future, there is a European equivalent that's being built. And whether we see the TMT or there's another telescope project called the GMT, the Giant Magellan Telescope, that would be built in Chile. These things are, you can imagine, they're enormously expensive and time consuming, but those are the plans.
Okay, we have time for only one or two more questions. It's asked, if the universe is 13.5 billion years old and it's expanding, it must be now at least 27 light years away. How do we know that, and how do we test it?
Yeah. So this, okay, this is very tough. I have a lot of trouble imagining this myself, and I certainly have a lot of trouble explaining it to classes. We think that the volume of space is infinite, okay? Not only is it infinite now, it was infinite from the time of the Big Bang. When the universe was born, it was infinite in volume, in the sense that there was no edge. What is not infinite, what is finite, is the so-called horizon, because we can only see what light has had time to bring us. And right now, the most distant thing we see is, this galaxy 13.5 billion light years away. So our horizon is getting bigger. As time goes on, more and more is entering our horizon, but it goes on forever, according to cosmology as we understand it.
Okay, with that, I think we will conclude the questions. Obviously, you might have questions on any of the enormous spectrum of topics that Ellen has discussed, and I'm sure she wouldn't mind receiving emails eventually asking about these questions. And I want to thank her on behalf of the LP Squared and of the New School for this remarkable talk. Thank you, Ellen.
And I want to thank you again for the opportunity to give it. And it's been a pleasure to talk to you and to hear your questions. And just, you can find me at the University of Wisconsin. I'm happy to take more questions.
Great. Well, that was a very special talk. And I think one of the things that was so special was the way you combined the personal with the scientific. And I know so many of your mom's friends and colleagues are on this webinar, and I'm sure that they are very proud. And I'm sure that they know your mother would be. So thank you very, very much. And thank you also to Fran DeLotte, who got us started on this path. And thank you, of course, to CUNY for the CUNY Graduate Center, our new home, who sponsors us. And speaking of which, please fill out the survey for this program, because it'll help us a lot in scheduling future speakers. And just in conclusion, I have a burning question that I'm going to email you, and that is the James Webb Space Telescope going to help us find life out there? So
it is certainly the hope of some of my colleagues, including Professor Zhang, whose picture I showed you. A big part of astronomical science now is really kind of getting into chemistry and trying to understand what biosignatures, how can you tell by looking at the atmosphere of a planet? We don't expect to see, cities or anything like that, but can you tell by looking at the atmosphere of a planet that it harbors life? That's a very active area right now.
good. Well, we're very hopeful. So thank you so much. And we will see you again on Fridays at 1 next fall. Okay, thank you, Ellen.
Bye.
Bye, everyone.